Hey there, and welcome to my lesson on the integral test and the test with p-series for convergence or divergence. So what you're seeing here is it's talking about things that we've already seen as far as how we can check for convergence or divergence with things that we've talked about before with the limit test for convergence or divergence, geometric series test for convergence or divergence. Not so much, I know it mentions the telescoping series, but we weren't really doing much in the way of convergence or divergence with that. So here, as a refresher, are the results of what we saw from our geometric series test. Essentially, if you have a geometric series and the constant ratio is going to be greater than or equal to 1, we can use that to justify that the series is going to diverge. And if the constant ratio was some fraction, absolute value of that number, as long as it's, less than 1, we would be able to justify that the geometric series would converge, and then we could use the sum of the finite sum of an infinite series for the geometric series, which you see, and again here I like seeing it as a sub 1. Oh, hello. That was unexpected. A sub 1. There we go. I like it when things work. And that could actually tell you what value that the series would converge to. The nth term for convergence, this is the one that had a may or may not situation that went with it. If the limit of the function or the limit of the sequence itself was not equal to 0, then we could say that the function would, or that the series, I should say, diverges. If the limit was equal to 0, then that's when we would be able to say it may or may not converge. At that point, we would need to know if it actually has a finite sum or if the sum diverges because it's unbounded. So coming together here, this is just asking us to see, can you review that information to determine whether or not a series is going to converge or diverge? And both of these are things that ideally you would be able to do based off of the information that you've seen in that lesson. But we're going to presume that we need a refresher just to make sure. And what I'm looking at in this example, I'm looking at A first. And to me, the sequence that I'm seeing, the 4n over 5n plus 1, that to me stands out to be as a geometric sequence. And I can rewrite the series to look like this, so it's a little easier to see it. Here we can have our A term to be 1/5. The constant ratio would be 4/5, and the constant ratio, that's what's going to be raised to the power of n. And so now we have our constant ratio. Oh, sorry about that. There were some announcements going on over the intercom there. So going back to the example, in this case here, the 4/5, that's your constant ratio. So here I'm going to say, since r, the absolute value of r, is going to be less than 1, what that allows me to say, what that allows me to conclude is that the series will converge according to the geometric series test. So I'm abbreviating here. You don't want to abbreviate on your answers, but here, because we're able to show that the r value is going to be less than 1, that we can conclude that the series will converge according to the geometric series test. So what about the next one? The next one here, to me, it doesn't really stand out as anything saying that we'll be able to kind of rewrite the sequence itself to show that it would be geometric. So since we do know how to do the nth term test for convergence, so I'll go ahead and do the nth term test here. So that means what we're going to do is we're going to take the limit as n approaches infinity of the sequence itself of this expression here, and you can either write it in terms of x or leave it in terms of n. Realistically, it doesn't matter. So here we're going to say 5n squared. Now, ideally, guys, you're going to be able to look at that and say, well, Mr. Piercy, that's just a rational expression. It's balanced. Its n behavior is going to go to 5 over 2. Yes. Again, if it is a multiple choice question, you don't have to provide any calculus justifications, but if this was a free response question, if it asks you to tell whether it converged or diverged, you would have to be able to do some kind of calculus here to justify that. So here I'm going to do my calculus. I'm going to say 5n squared plus 3 over 2n squared. And if I just do my direct substitution on this one, we're going to get infinity over infinity, which means that since that's our indeterminate form, we can apply L'Hopital's rule. Or we can, in this case, this is what I'm going to do, is I'm going to just multiply by the reciprocal of n squared to the top and bottom. So here I'm going to multiply by 1 over n squared to the top and bottom, and that will give me 5 plus 3 over n squared over 2, and that'll take care of the indeterminate form as well. And what we're going to see here now as n goes towards infinity, that's going to approach 0, and we're winding up with our limit to be left as 5 over 2. So here in this case, because the limit is not equal to 0, so now we've established what our limit is. Now again, does it converge or diverge? So well, not according to, we'll say by the nth series test, this series will diverge because the limit as n approached infinity was not equal to 0. So there's our justification. Here's our answer to, or here's the calculus work that justifies it. Okay, and here's our explanation that supports our answer. Okay, so that's our quick review over the geometric series test and the nth series test. Now, one of the things that we're going to finish taking a look at in this Unit 9 is the remaining ways that we can test for convergence of different types of series. So we've already talked about the geometric series, and we've already talked about the nth series test. This one, according to the title of the note, should be pretty obvious. We're going to be talking about the integral test for convergence and the p series test for convergence, where the rest is going to be seen in a separate video. So what we have, again, those of you that happen to be following along with your notes with this, if you just happen to be a random person on YouTube looking for stuff to help you with this material in calculus, you can certainly copy this stuff down. But students from my class, you should have this stuff in your notes, and what we're going to be looking at here is kind of it's a very short, or it's meant to be a very short exploration as to show what the integral series test for convergence does. So here, this is going to kind of take us back to some things that we've seen before. Now, what we're looking at here in the function is we have 1 over x squared. which of course is the reciprocal squared parent function. And what we're seeing in the graph that's being provided is just what we would have it as a series, where we're just looking at it from 1 to infinity. So filling in the table here from the expression that we would have, I would have when x is 1, y is 1. When x is 2, we have 1/4, and then 1/9, 1/16, 1/16, and then 1/25, and so on, right? So what it's telling us to do here, it's asking, draw the right-hand sum with 4 partitions. So we're going to go back to what we were doing with Riemann sums over the interval from 1 to 5. So starting at 1, we're going to draw a right-hand rectangle here. And we'll draw a right-hand rectangle here, and a right-hand rectangle here, and so on. And you just get as close as you can for those and see what you end up with. Well, what it's asking us to do, it says find the, so again, Riemann sum is asking us to find the area, and essentially here in this first rectangle, this would have an area of 1/4. This would have an area of 1/9, 1/16, and 1/25, respectively. So that's essentially what we're finding the sum of. So the sum of those rectangles, 1/4 plus 1/9 plus the 1/16 plus the 1/25 rectangle is going to have a sum, and here I'm just doing it on my calculator, of approximately 1.434 square units. Well, what it's asking us to do here, it's on part 2, it's asking us, can you find the, actually no, I'm reading my notes wrong. Haha, I am reading my notes wrong. It is 0.434. 0.434. So hopefully if you're getting a different number and you're like screaming at your screen there, yeah, I'm looking at my notes wrong. Didn't write them out very well, I guess. But it's asking us now for the second part, find the 5th partial sum of the series. Now in this case you can kind of see the 5th partial sum from 1 to infinity is in this case when n is 1. So here, let's go ahead and write it out. N equals 1 to infinity. So in this case, when n is equal to 1, my first term is 1. And then we have all of those other terms, 1 to the 4th plus 1 to the 9th plus 1 to the 6th, or 1/16th and 1/25. And that, the only difference between what we did on 1 and what we're doing on 2 is the inclusion of that 1, and that's where I'm getting the 1.434 sum. Now it shouldn't take any real effort here to justify that what we're doing so far with the Riemann sums, those were very much introduced to just as a general idea of how we can approximate the area under a curve, but they were either an overestimate or an underestimate depending on, one, the type of rectangle that you used, right hand or left hand, and whether the function was concave up or concave down. So it should be pretty apparent that the rectangles that we're looking at here, let me see if I can kind of fill it in a little bit without it totally obscuring everything. So here, this is what we're looking at for our, let me see if I can get a different color, make that a little nicer to see. Let's try this yellow color here so you can still see. There we go. There we go. I think that's a little easier to see. That shaded area is essentially what we're using, and that's our underestimate because, of course, we're missing out on all of this area here. We're missing out on all of this and all of this and all of this. So because the function is concave down and we're using the right-hand rectangles, we're going to have an underestimate. Well, what it's asking us to do now is on part 3, let's take a look at the actual integration from 1 to 5 here and see what we end up with that. Well, looking at the integration here, I'm going to just rewrite the integrand, 1 to 5, as x to the negative 2 power, just because my mind will perceive it a little bit easier when I try to do the antiderivative on this one. When I do, I wind up with a negative 1 over x evaluated from 1 to 5. So doing that, let's see what we get here. We're going to say negative 1/5 minus negative 1 over 1, so that'll be a plus here. 1 over 1 is just 1, and so that is going to work out to be a positive 4/5, or as a decimal, 0.8, whichever you prefer, which again is going to confirm that the actual area and the estimated area that we got from 1 to 5, meaning those 4 rectangles, that those were going to be an underestimate. Now here, this is where things are going to start to get a little, I don't want to say funny or tricky, but this is where things are going to start to get a little bit more in depth as far as what it's asking us to understand for the integral series test for convergence. Well, what we can look at here is if we take the summation of n equals 1 to infinity of 1 over n squared, this is going to look at the first rectangle. Now the first rectangle that I'm really referring to, this is when n is equal to 1. So when n is equal to 1, the rectangle that we're talking about is really this guy right here. And I think I might be shorting myself. Yeah, I am shorting myself some. This is the rectangle that we're really looking at for the first rectangle. Okay? And that is going to be adding to n equals 2 to infinity of 1 over n squared, and that's where we're going to wind up getting all of the sum of the rest of the rectangles. So we know that the sum of the, looking at the first rectangle has an area of 1. So that first rectangle has, in this case, it's going to be an area of 1 plus the sum of the other rectangles, 1 over n squared. Or if you want to look at it in terms of a function, you can think of it as x squared. Okay? But this part right here is what I'm looking at as the sum of those 4 blue rectangles. Sum of my rectangles. So what we're going to be looking at here, moving on, is what we were able to show with the integration here. So if we start doing the integration of the entire part, that's going to be looking at all of this overall area, the actual area underneath the arc, not the underestimated values. Well, because they're underestimates, without even having to do the sums, we can conclude that the integration and the approximates that we got with our Riemann sums, the integration is going to give you a value that's going to be greater than the Riemann sums. So what we're looking at here is I can take those. Let me move this down a little bit because I am going to need a little bit of space here. So again, those of you that are following on with your notes, we're going to get tight on space a little bit. But here, we can conclude at this point that what we have 1 plus the sum of these rectangles of 1 over n squared, they will be less than the first rectangle, which also still has an area of 1, plus the improper integral from 1 to infinity of 1 over n squared dn. And again, if you're writing all of this stuff in terms of x, you would write that as dx instead of dn. Well, here, what we're going to do now is understand that what I'm going to do is I want to take the limit of the improper integral here, and I'm going to say, okay, well, if I take a look at that limit, let me go ahead and go to a different color here. Maybe something that's a little different. Let's see, if I take a look at the limit for the improper integral here, we're going to say the limit as, and I'm going to use the term b, as b approaches infinity of 1 to b for my improper integral there, and I'll say 1 over n squared dn. Well, that is going to translate when I do my anti-derivative. I'm going to get negative 1 over n, and we're evaluating it from, or I guess I'm going to nx, it really doesn't make a difference, and we're evaluating it from 1 to b. So that continues, and I'm going to just keep going to the right here so I don't have to keep going down all the time. In this case, that's going to be the limit as b approaches infinity of, doing my substitution now, we're going to get negative 1 over b minus negative 1 over n, which in that case will be a plus 1, or a plus a value. And in this case, I'm going to say 1 over 1. And as we evaluate this going towards infinity, we can see that this will go towards 0 as b approaches infinity. So the limit of this expression is 1. And what that's going to allow me to show is that now what we have, we can take this and take it and put it here for this expression for the indefinite integral, or for the improper integral, and that will allow us to show that in this case the sum of the series, let me pick another color here, the sum of the series, because we know the sum of the series is going to be 1 plus these other pieces here, the sum of the series is going to be from 1 to infinity of 1 over n squared. It's going to be less than 2. Now what that allows me to conclude is that this value right here, that 2, that is the upper bound of the function that we're seeing, because again, we're looking at it as an underestimate. So the 2 is going to be the upper bound of what we could go to for our series in this case. Now, let me go ahead and write this down. I'm going to go ahead and pause the video and write this down, and then you can add it to your notes here in a second, because you don't need to actually watch me write it. Okay, so here it is written out. This is what I want you to understand. Because the series itself does have an upper bound, meaning that the overall integration, the sum of everything that we could get, does have an upper limit. That allows us to say that because it has an upper limit, the series converges, therefore it is bounded. So if the sum was divergent, meaning it went to infinity, then we would say that the series is unbounded. And this is essentially what we're trying to show for what the integral series test does for us, how we use it to show when something is going to converge or diverge. So the next part here, oh, and we can skip this, I just kind of placed everything on one page so it was easier to do. This is what the conclusion of the integral test is going to be saying, okay? Now, the integral test itself, the conclusions are what we're seeing, you know, kind of here and here. Now, there are some conditions on the integral test. The integral test, in order to be able to use it, your sequence must be continuous, it must be positive, and it must be decreasing on your interval from 1 to infinity. Okay? So those are the three things that we're going to be checking. Now, here, what I want to kind of, let's see, where it says in that first part of the conditional statement, if the improper integral of f of x dx is convergent, where it's saying it's convergent, it says that it's approaching a specific number. So we can look at it as the improper integral f of x dx. If it equals a specific number, then that means that the function is going to be, or the series itself will be convergent. Now, if the integration, the improper integral from 1 to infinity of f of x dx, if that goes towards infinity, meaning it's the improper integral is divergent, then the series itself is going to be divergent. Okay. Now here, it is giving you a little note here at the bottom. The most common use is in the p series. And we'll take a look at what the p is. P meaning power. We'll take a look at that here in a little bit. But now that we've talked about it, now let's see, can we apply it? And I want you to be mindful. The two examples that we have, they look similar, but the numerators are different. So please be mindful of that. But I'm going to do one, and then I'm going to ask you guys to try and do the other one, just to make sure that you understand what we're looking at here. Okay, so I'm going to do part A, and what we're looking for. This is the checklist that I kind of go through in my head. First of all, according to the integral test, because that's what we're doing, is the sequence continuous? And again, when we're looking at it continuous, we're looking at it on the interval from 1 to infinity, because that's what a sequence looks for. Okay, so is it continuous? Is the sequence, or is the series, the numbers that we're going to be getting, is it positive? And is the overall sequence decreasing? So those are the three things that we're looking for to check to see, can I even use the integral test? Because if it fails even one of these things, then the integral test doesn't work. Now the one thing that I'm going to ask, that I'm going to kind of point out here, whether it's decreasing, we can kind of look at the numbers of the actual sequence itself, or we can look to see, is the derivative of that function, is it going to be less than 0? So if I took the derivative, if I look at it in terms of a function, if I say if the derivative of it, if it's going to be negative, that will allow us to know that the sequence itself is decreasing also. Okay. So is it continuous? Let me go ahead and transition to a different color here. So, well, what we're seeing here, we are not going to have any kind of problems in the denominator. The only value that we might have an issue with is if we were able to get a -1, but since we're squaring everything, that it's not possible for n to produce a negative value. So from +1 to positive infinity, it will be continuous. Okay. Again, the numerator is positive. We're adding 1 in the denominator, and we're squaring something in the denominator. So again, it doesn't make a difference what numbers we substitute in for n again, sticking to that interval, everything will be positive. Now, is it increasing or is it decreasing? Now, personally, I think probably the numbers are going to be a little bit easier to see because when n is 1, we can get a 1/2. When n is 2, I'm going to get a 1/5. When n is 3, I'm going to get a 1/10, and so on. 1/17, 17th for n is 4, and so on. So we can clearly see that those are decreasing. If I were going to look at this as a function, the derivative of this particular function will be negative 2x, or 2n, however you want to think of it, over n squared plus 1 when we do the quotient rule. Okay, so because we do have that negative in the on the overall fraction, the derivative is less than 0, so it's definitely decreasing. So either of those two things we can look to check to see is it decreasing here. Okay, so it does hit all of the things that we need to know for the integral test itself. So now let's go ahead and start looking at it. What I'm going to do is I'm going to look at the sequence itself as a function. So I'm going to set it up as an improper integral from 1 to infinity of the function, and in this case I'm going to say 1 over x squared plus 1 dx. Okay, so for my improper integral, again, we have to treat it the way, do our integration the way that we have been doing it with improper integrals. I'm going to look at it in terms of the limit as b approaches infinity. A lot of people like to use t here. If you want to use t, it's fine. And we're going to say from 1 to b of 1 over x squared plus 1 and dx. So now that's how we set it up to do the actual integral. Now, one of the things that I want to kind of illustrate here, this, particularly looking at the denominator and the fact that the numerator is a 1, what we're looking at here, this hopefully is going to jump out at you and say, here we're going to be looking at something as inverse tangent. Okay, so if you don't remember what inverse tangent is, here we're looking at du over a plus u squared, and the u in this case would represent the x. Remember the integration of that would be 1 over a times arctan, or tan inverse, however you want to write it, of u over a. So there's that in case you don't remember it. All right. Now, in this case, the u term is going to be x, the a term is going to be 1. So if I take the derivative of u, that's going to be my dx. So when I take the integration of the 1 over x squared plus 1, here I'm going to end up with the limit as b approaches infinity. In this case, because a is 1, we're going to get 1 over 1, so I don't need to write the 1. Tan inverse of u, in this case, is going to be the x value over a, which is 1. So this is really going to just be, I don't need to write it as a fraction. I can just write it as inverse tan of x. And we're evaluating it from 1 to b. So now we're going to end up with the limit of b as it approaches infinity, inverse tan of b minus tan inverse of 1. And here we do need to remember a little bit about where tangent is going to, or the inverse tangent stuff off of our unit circle here. In this case, what we're going to see as as b goes towards infinity, in this case, we're going to get pi over 2 minus pi over 4 at 1. So all of that simplifies to be just pi over 2. So what that means, what we're doing is, again, the integral test for convergence or divergence. If the integral test, which is what we've been doing in this kind of, I don't know, brownish orangish color or whatever, that is show. Oh, and I wrote my denominator wrong. It's 1/4. 1/2 minus 1/4 is 1/4. Because we're approaching a specific number, because we're approaching this specific number, that means the series as n approaches, or as n is equal to 1 to infinity, of 1 over n squared, that series is converging, my marker doesn't want to write, converging by the integral test because, what did they actually say here? Because this improper integral 1 over x squared dx equaled a specific number, pi over 4 in this case. That may be a little bit overkill for the justification. You need to show that it does approach a specific number, and then you really can, all you need to be able to tell me really is that part at that point. It's converging because it approached that specific number. But again, I just try to be thorough, make sure everybody understands what the explanations are going to be. Okay, so you guys go ahead and pause the video at this point. Try working out example B, and when you're done, hit play, and the answer will magically appear on the screen for you. Maybe? Is it working now? Sorry, I apologize if you heard some rambling. My computer is having a hard time focusing this afternoon. So let's go ahead and take a look at the second example here. Again, we're doing the integral test for convergence. We're checking to see, is the integral going to be, or is the sequence going to be continuous, positive, and decreasing? And in this case, I'm checking yes on all three of them. Here I'm just showing you what the derivative of the expression would be. Because the numerator is going to be 1 minus 2x, and we're only looking at positive values, the numerator will always be negative. So yes, the function will be decreasing because the derivative is negative. So if we look at the expression as an improper integral in terms of a function x over x squared plus 1, we look at it with our improper integration, where we say the limit of t, in this case is the variable that I'm choosing to work with, approaches infinity. We'll say x over, and I forgot to write my plus 1 here, plus 1. What I'm going to look at here is I'm looking at the denominator overall as u substitution for this case, because if I take the derivative of the denominator, we can see that we should be able to get an x dx in the remaining part of the integrand. So I am going to use u substitution here. We're not going to try and do trig inverse like we did on the previous example. We wind up with 1/2 of the integral from u to t, or from 1 to t, of 1 over u du, which gives me 1/2 natural log u when I take the antiderivative. Separating it to be natural log of u minus natural log of 1 in this case, or natural log of t minus natural log of 1 in this case, is going to give me x squared minus 1 for this one, and natural log minus natural log of 1. Of course, natural log of 1 goes to 0. So even though we have that 1/2 constant on the outside, it doesn't make a difference because natural log of infinity is going to go to infinity. Therefore, the series diverges according to the integral test for convergence. Now here, what we're looking at on this is asking us to do a comparison, and really this is going to be kind of a proof that we're going to be looking at for why something is going to converge in one case but not converge in another case. And this is really talking about the harmonic series. Why does the harmonic series 1 over n diverge when 1 over n squared converges? So let's take a look here. Let's explore why 1 over n squared converges, but 1 over n does not. Consider the following grouping in terms of the harmonic series. Now, this is kind of a simplified version of what was done a long time ago as a proof for why the harmonic series does converge. And they're looking at particular groupings. And kind of towards the end, I'll kind of illustrate what the proof was meant to do. But looking at the groupings here, I'm going to look at this one is group 1, this one is group 2, these 4 fractions is group 3, and so on. And part A, it says, show that the sum of each group of fractions in the series is more than 1/2. Okay, well that's easy to do. So the group 1 that I have, group 1, well it's just, 1/2. So we're looking for each one, show that the sum of each group of fractions in the series is more than 1/2. And I think that is really meant to be looking at the groups after the second term. But let's take a look at the group 2. So group 2 in this case, if I say 1/3 plus 1/4, that is going to be 7/12. Or as a decimal, that would be 0.583. I have such a hard time writing threes for some reason. 583 repeating. If we look at the third group, the 4 fractions that are there, as a fraction, that's going to be a sum of 533 over 840, or about 0.635. And the fourth group that I have, the sums from 1/9 to 1/15, that one, I'm not even bothering to put this one in a fraction. This one's going to be about 0.600. So yeah, the sums of the individual groups after the 1/2 are definitely more than 1/2. And so what that is kind of illustrating, and it's going to it is going to ask us later on, to look at this, but because of each individual group, the group 2, the group 3, the group 4, and if we continued with it, we would get here. Now I want to illustrate, I don't know if I was just having an off moment or something. Here I'm getting 0.600, but at one time I also got like a 0.66, and I'm not entirely sure which one I was expecting to see. I'm expecting to see growth, so I thought I was going to be getting this, but for some reason my calculator kept giving me that. So just understand, but yeah, the growth is going to continue from group to group to group. Now, I'll explain where these groupings kind of came from here momentarily, but each successive group does have a sum that's greater than 1/2, and because those sums continued to increase, that's why the overall harmonic series is going to be divergent, because the actual sum is going to be unbounded. Well, now let's take a look at the terms in the series 1 over n squared. And it says, in the term, or group the terms after 1 in any way that you like. And so you can do it however you want to. And show that they are never going to be greater than 0.65. So in this case, I'm looking at, let's just look at the first 2. I'm going to look at the first 2 here. And I'm going to say that's 1/4 plus 1/9. And again, you group them however you want to. And if I take the sum of those, I'm getting on my calculator approximately 0.361 repeating. And then if I go to the next group, so the next group that I'm looking at is I'm kind of just expanding it to include the 3 fractions here. So I'm looking at 1/4 plus 1/9, plus the 1/16th. And what we're going to get here is I was getting 0.424 on my calculator. And play around with them as in whatever, groupings that you would like to do. And ultimately what you're going to recognize is that because the fraction value, the denominator gets bigger. As the denominator of fraction gets bigger, the overall value of the fraction drops. So as we continue, that denominator is going to get smaller and smaller, 49, 49, 64, 81, etc. It's going to get closer and closer and closer to 0. So when we were looking at the groupings of the harmonic series, we were recognizing that the sums were continually increasing, meaning that they were going to be greater than 1/2. Specifically is what they were asking us to look at. But with n squared, because the denominator continues to get bigger and bigger and bigger, the overall fraction value gets smaller and smaller and smaller. And so the sum of those things never really gets any bigger than any particular value in the series. In this case, they're asking us to compare it to 0.65. So this one here has a convergent sum, but the harmonic series does not. And I've kind of been explaining why. You can write down your own explanation here if you want to, but I'm going to go ahead and pause the video and I'm going to kind of write some stuff down here to show you what we were looking at for the groupings. Okay, so hopefully my computer will cooperate. So okay, and here is the summary of what we're looking at for the harmonic series, why it never converges. So the grouping that you're seeing here, this is just a very brief summary of the proof that was established, I don't remember when, a long time ago by some French mathematician. It says, replace the terms in the sequence of 1 over n with the smallest powers that are less than or equal to 1/2. So as we move through the sequence of 1 plus 1/2 plus 1/3 plus 1/4, etc., we start to see things that are going to be less than or equal to 1/2. So when we get to the 1/3, that's where we start to replace powers, or we start to replace those terms with things that are going to be less than or equal to powers of 1/2. So that's where we get the 1/4 and the 1/4. And the next 4 terms get replaced with 1/8, 1/8, 1/8, 1/8. And then the next set of terms would be replaced with 1/16 plus 1/16. And I think there's going to be like 16 of them? No, that doesn't sound right. But there would be a whole bunch of 1/16ths. And the sum of each of those things all works out to be 1/2 plus 1/2 plus 1/2 plus 1/2 as we kept going. And of course, if we take the sum of 1 plus 1/2 plus 1/2 plus 1/2 plus 1/2 ad infinitum, then that shows that, yes, the series is going to converge. Now, or diverge, I mean. Now, what I wrote in purple kind of on the right, that's more specific to what we were looking at up in part A. After the second term, each grouping had sums that were greater than 1/2. That means if we take the sum of that particular series, it will grow forever, showing that it is actually divergent. And that's what's unique about the harmonic series. Are you going to have to prove it? Probably not. But here you go. Here's some explanation as to why it diverges and n squared will converge. Now this is actually getting into what is known as the p-series. Here, oh wait, this is, sorry, I adjusted this and I forgot to delete this page and I forgot. Here we go. Here we're looking at, this is where we're getting into the p-series, a series in the form of 1 over n to the power of p. And of course, n can be any number. That's called the p-series, where p is going to be a positive constant. Now, we can have, a whole bunch of different a whole bunch of different things for p-series. 1 over n. 1 over n is a p-series. Of course, 1 over n squared 1 over into the third power and so on. Those are all going to be different types of p-series functions. Okay, so the harmonic series is a p-series. But what this is going to allow us to do, and this is here, the harmonic series, and this is the one that's really going to establish, this is kind of the one oddball one that kind of has its own particular thing where in this case if p is equal to 1, the harmonic series. Well, we've already established that for the p series, for the harmonic series, that one is going to diverge. So in a p series sequence or series, p series, yeah, if the p value that we're looking at is going to be equal to 1, that is going to diverge. Okay, so here it diverges. Now, what happens if it's going to be greater than 1 or less than 1? Well, we've already seen what happened when something was greater than 1. That's where we looked at 1 over n squared. In this case, the p-value is going to be 2. It's going to be greater than 1. So that one showed that it does have a finite sum, and that one will converge. So what about between 0 and 1? You know, like something to the 1/2 power. Well, those are also going to diverge. And this is what we can look at as another method to justify whether a series is going to converge or diverge. If it's a p-series function or expression that we have, we can look at the value of p and use it to justify whether the series will converge or diverge. And here we're getting into a couple of examples of what we want to do. So again, I will go ahead and do one for you and ask you guys to try and do one yourself and see what you end up with. Now looking at this one here, I'm going to rewrite this particular series. So if I look at this into the 1/2, if I look at this as n to the 1/2 power, this is n to the 1 power. So this works out to be, you know, adding your properties of exponents there, 1 plus 1/2 gives me n to the 3 over 2 power. Okay, now this is a p-series. Okay, this is a p-series. So there's really not a lot of work that we need to look at here. We're looking to see what is the value of p. Well, in this case, p is the 3 over 2. And since 3 over 2 is greater than 1, we can say since p is greater than 1, this series will diverge, or I'm sorry, will converge. And that's really all we need to do on a problem like that. So go ahead and try working out the next one if you want to, and hit pause and look at the video. But again, this one's going to work out pretty similarly. The radical, I'm going to convert that to be n equals 1, infinity. So I'm going to convert the radical into an exponent, and that'll be 1/3. And again, this is a p-series. In this case, p is equal to 1/3. So since p in this case is less than 1, but it is greater than 0, this series will diverge. By the p-series test. So let's take a look. We've got a couple more examples here. Now the next example here can be done using the p-series. You can say that, again, if you look at it in terms of converting the radical into an exponent, we can look at it literally the same way that we did a second ago. This is going to be n to the 1/4 power. So in this case, because p is less than 1 but greater than 0, this function therefore is divergent by the p-series. Okay, now I am going to go ahead and take a look at this one here in a different way. I'm going to also look at this one using the integral test. Okay, just because these are things that we've been talking about, and I want to make sure you have enough examples to look at to help you understand how we can do these. So we've already established that it's going to be divergent according to the p-series. So if we do everything right with the integral test, it should match, okay? So remember, what we're looking for here is we're looking for, in the integral test, we're looking to see what is going to happen to the limit. Is it going to approach a specific number, or is it going to go towards infinity? Okay, so here, let's go ahead and take a look at the integral test. I'm going to look at this in terms of a function. So I'm going to say my improper integral from 1 to infinity of 1 over x to the 1/4 power dx will be equal to the limit as t approaches infinity of 1 to t 1 over x to the 1/4 dx, or x to the negative 1/4 power if you prefer to make it easier to see how you're going to do the integral. Let me go ahead and just do that, I guess. X to the negative 1/4 power. And now we can find the integration of that, and I'm going to get the limit as t approaches infinity of, in this case, I'm going to have a 4/3 times x to the 3/4 when I do my antiderivative. And we're evaluating it from 1 to t again. So the limit as t approaches infinity, here 4/3 will get multiplied to t to the 3/4 power minus 1 to the 3/4 power. And this is where we do our substitution for infinity. So here, the 1 is negligent or insignificant, because when I substitute t to the 3/4 power, that's going to times 4/3. All of that's going to go towards infinity. So the limit here is going to go towards infinity, which again, here we can say, therefore, this series is divergent by the integral test. Okay, so they match. They agree with each other. Yeah, they're both saying it's divergent. Now on this last one here, this one is not going to be a p-series, because what we're looking for the exponent to be in a p-series is an actual number where p is going to be a positive constant. So in this case, this one cannot be done using the p-series. So you have to use, in this case, what we're going to use is the integral test. So feel free to go ahead and try and pause the video and work it out on your own and see if you can determine whether this is going to be convergent or divergent according to the integrals test. I'm going to go ahead and get started. We're going to look at it in terms of a function. So I'm going to say the integral from 1 to infinity of, and in this case I'm going to just write it as 1 over n. Nope, not 1 over n, 1 over e to the n. There we go. Get your head in the game. E to the n, or e to the x dx if I'm looking at it in terms of a function. So here I'm going to have my improper integral. Nope, my limit. My limit as t approaches infinity, 1 to t, 1 over e to the x dx. Now, if you prefer to keep it as e to the negative x, you're more than welcome to, because that might make it a little easier to see what the antiderivative is going to be. Okay, 1 to t e to the negative x dx. So limit as, not t, golly. The limit as t approaches infinity. In this case, the antiderivative of e to the negative x is going to be negative e to the negative x, and we're evaluating it from 1 to t. So here, limit t approach infinity, and we'll go ahead and do our substitution, and I'm going to say in this case we'll go with negative 1 over e to the t power minus negative e, so this will be a plus 1 over e to the power of 1. So as we go towards infinity, we're going to get 0 plus 1 over e. So the limit is just 1 over e, and therefore it is convergent. Okay, this is going to be convergent because the limit approached a specific value, so therefore converges by the integral test. Now this one's not asking us to do it, but 1 over e to the power of x, that's actually going to be a geometric series. So if I really wanted to, I could know what the series would, since I know it's going to converge, I can actually determine what it's going to converge to by saying a sub 1 over 1 minus r, and in this case that is going to work out to be 1 over e minus 1 without using a calculator, just leaving it as an exact number. That's the number that it would actually converge to. So a couple more examples here, and I will go ahead and start taking a look at this one here. The next one's going to get a little bit challenging. I think it looks weird, but I'll help you out with it and make sure that everybody's going to be in good shape. So let's take a look at the function that we have here, or the series. Now pay attention here. They're starting at 2, and they're not starting at 1. It's not really going to make a ton of difference here, but one of the things that you want to make sure that you recognize in the denominator on this example is that, I guess I'll keep using that blue color, is that in this case, the denominator is going to be the difference of two squares. So here n equals 2 to infinity. So I can look at this as 1 over n plus 1 times n minus 1. Okay? And looking at that, now here, this is not going to be a p-series. This has to be done using the integration or the integral test. So according to the integral test, if I'm going to have to take the derivative, or sorry, the integral of that expression, that should tell you that we're going to be doing partial fraction decomposition. So if I look at this as a function again from 2 to infinity in this case of 1 over x plus 1 times x minus 1 dx, then we're going to look at that overall using our partial fraction process, where I'm going to say this is going to be a over, I don't need parentheses here, x plus 1 plus b over x minus 1. And let's see what we end up with here. So looking overall at the overall thing, if I multiply with the common denominator, I'm going to get 1 is equal to a times x minus 1 plus b times x plus 1. So now we have to figure out the values of a and b. So if I make x equal to a negative 1, then that will give me an a value of negative 1/2. If I say the x value is going to be a positive 1, that will give me a b value of a positive 1/2. So here, what we end up with is from 2 to infinity, and now we're looking at negative 1/2 over x plus 1 plus positive 1/2 over x plus 2 dx. So according to our integral test, we're now going to take the limit of that. The limit as, here let's say a, as a approaches in infinity. So we'll do our indefinite or our definite integral from 2 to a in this case. 1/2 negative over, and that didn't show up very nicely. Let's try that again. Negative 1/2 over x plus 1 plus 1/2 over x minus 1 dx. And now we can do the antiderivative of that. So here, when I do the antiderivative, we'll have the limit as a approaches infinity of negative 1/2 times the natural log of x plus 1 plus 1/2 times the natural log of x minus 1, all evaluated from 2 to a. Okay, so now let's see what we get here. Now, looking at the values here, if I factor out a negative 1/2, or I'm sorry, if I factor out a 1/2, let's go ahead and just limit as a approaches infinity. Let's factor out our 1/2 as a constant, and the expression on the left is going to be negative and the expression on the right is going to be positive. So according to our properties of logarithms, I can rewrite that as the natural log of the x minus 1 term over the x plus 1 term, again evaluated from 2 to a. And now I think we can go ahead and do our substitution because we just have that one log term. It'll be easier to evaluate. So the limit as a approach infinity, 1/2, and here I'm going to say the natural log of, what do we have, a minus 1 over a plus 1 minus the natural log of 2 minus 1 will give me a 1 in the top, and 2 plus 1 in the bottom will give me a 3. Okay. And so now we can do our substitution for as a goes to infinity. So here as a goes to infinity for the logarithm here, this is going to approach 0. And so now we have 1/2 times the negative natural log of 1/3. So we can write that negative times negative, nope. I think I might have lost a negative, yeah, I did lose a negative sign somewhere, I think. I hate it when I do that. It happens, trust me. Yeah, I should have factored out here a negative 1/2. Negative 1/2. Sorry about that. And so now the negative 1/2 times the positive, or the negative 1/3 log, that negative log of 1/3, that will give me a positive natural log of 1/3. Well, we'll work it out. Positive, here, again, we're looking at some properties of logarithms, and I want to make sure, I don't want to skip it in case anybody forgets. Let's see. No, we'll just leave it like that. We don't need to worry about converting it into a radical or exponent or anything. Sorry I'm rambling, but this would just be working out to be natural log of 3 over 2. Okay, so there's the limit. And because the limit approaches a specific number, we can say that this will converge according to the integral test for convergence. Oh man, we got a lot of work on that one. Now the last one here that we're going to look at, the last one here is actually going to require a little bit less work, but it's going to definitely be a little bit more daunting just by looking at it. You just look at it and say, oh, that looks horrible, I don't want to do it. But if we look at the natural log times natural log of n, if we take its derivative, we can recognize that that's going to be n times the natural log of n. So what I'm looking at overall here is I'm looking at this to be u. So I can do u substitution on this. So I'm looking at u to be 1 over, actually, no, I don't want to look at 1 over. I just want to look at the denominator. Let's trade that up a little bit. I just want to look at the denominator here. So if I look at the denominator of u to be the natural log times the natural log of n, the derivative of that, du, is going to be 1 over the natural log of n times 1 over n. Or, more clearly, that is going to be 1 over n times the natural log of n, which matches what we have here. So this is going to be our du. This right here is u. So now we can look at it in terms of doing u substitution. So let's get started on that, and let's pick something that's not going to blend with everything else here. Let's do green. I haven't done green yet. All right. So looking here, and I guess I can probably just take this stuff here and just move it out of the way because we don't need it for this problem. There we go. So looking at the series, we're starting at 3 in this case, 3 to infinity. And we're going to look at this to be, here we have 1 over u du. And so looking at this as a function, here I'm going to say the limit as t approaches infinity of the definite integral from 3 to not infinity, from 3 to t, and that would be 1 over u du. And here we can go ahead and do the antiderivative, which would be limit t goes to infinity of the natural log of u. And I know I sometimes I have a bad habit of writing. I don't like doing the natural log with the lowercase l because to me it's just too close to 1. That's why a lot of times I do it with a capital L, just in case you're wondering why I'm switching from lowercase l to capital L. It's just kind of a personal preference, okay? But it doesn't change anything about the problem, lowercase l or capital L. And we're doing it from 3 to t. So here we're going to go, at this point, we're going to say, let's go ahead and put our u value back. So in this case, we have our limit as t goes to infinity. So now let's put our u value back. So I have the natural log. Now for u, we're going to put the natural log of n, or natural log times natural log of n. Okay, and we're still going from 3 to t. And now let's plug in our value for t wherever we have our n term, which 3 and n. The only place it's really going to get substituted is right there. Too many n's in this problem. So the limit as t goes to infinity natural log of natural log of natural log of t. There we go. We got something besides n working for us. And then we're going to say minus the natural log of uh, natural log of 3. God, too many natural logs here. I don't like this problem. Okay. So looking at it, as t goes to infinity, then all of this stuff here, I don't want to do blue. As t goes to infinity, all of this is going to go to infinity. Now, the natural log of natural log of natural log of 3, that's just going to work out to be a constant. So an infinity compared to a constant, the constant is irrelevant. So in this case, the limit will be infinity, and therefore this series will diverge. And that's going to wrap up the examples that we have for the P-series test and the integral test. P-series test is going to be pretty helpful if you can use it, because you don't need to necessarily do a lot of work to justify it. You can just look at the value of the exponent, whatever that positive, number happens to be, and say if it's going to be greater than 1, then you're going to say it's going to be convergent. If it's less than or equal to 1, or less than or equal to 1, then that's going to be where the p-series would diverge. For the integral test, again, we're looking to see if the limit, if we look at the sequence as a function and we evaluate its limit as an improper integral, if it approaches a specific number, we can say that it converges. If it approaches infinity, we say the function or the sequence will diverge. And that is about all we have for this section of material. So thank you for your patience. Thank you for watching. I hope you found some beneficial information out of this and got enough examples to help you with whatever problems you need to look at. And until next time, guys, thanks for watching. Take care, and we'll talk to you soon.